Okay, well, let's get started. So first presentation is by Matisse from Bank of Spain. Yes, please.
Okay, can you see my slides?
Yes.
Yeah.
Okay, so this paper is joint work with Pablo Aguilar, Corina Aguileri, Matias Pache, and Alberto Ortazun. I'm Matias Pache, and you know the usual disclaimer apply here. The views I'm going to express are from me and not for the Bank of Spain or the Euro system. So this work is called "Can News Help to Measure Economic Sentiment?" An application in COVID time. So we all know that knowing how the economic activity is doing, it's very important in order for the policymaker in order to apply their future policies or the future policies. Sorry, but one of the best measures we have about the economic activity is the GDP, as all we know, but it has the problem that is compiled on a quarterly frequency with a lag and is released with a lag of 30 days. So in general, more timely indicators are used, in general monthly indicators, and among them, the soft indicators, which are based on surveys, are used a lot in order to follow how the economy is doing each month, and in order to use this kind of indicators in order to nowcast or forecast the GDP. You know, so one of the most used indicators based on surveys, which is used a lot, is the economic sentiment indicator published by the European Commission, which basically is built on 5 confidence indexes. So it has some share of it is built based on the industry surveys in construction, in confidence in construction, confidence in service, confidence in services, confidence in retail, and consumer confidence, and it's released between the 27th and 29th of the month. So tomorrow we will know how the economic sentiment indicator was for Spain during the month of October. You know, this kind of indicators widely used. We use a lot. We include this indicator in our nowcast models at the Bank of Spain. So back on March, when the COVID crisis emerged, we were waiting for this particular indicator because it was the first one in order to be released for Spain in order to see how the economy was reacting to the crisis. But you know, at that moment in March, the Spanish government put a lockdown on the economy on March 15. So the last 15 days of the month were affected by this lockdown. When the economic sentiment indicator for Spain was released in March, we observed at that moment that the indicator didn't react as much as we expected at that moment. So, and this is because there are some inherent limitations of the economic sentiment indicator, which were particularly important during the COVID, the outbreak of the crisis. First of all, the economic sentiment indicator is based on surveys which are conducted during the first 3 weeks of the month, or maybe the first 2 weeks of the month. For example, for consumers, retail, or services, in March of this year, the surveys were conducted between the 2nd and the 12th of March. And for industry and construction, the surveys were conducted between the 2nd and the 23rd of March. So for these three, for consumers, retail, and services, it didn't cover anything about the lockdown, which was put on by the government by March 15, and it only covered 8 days of the lockdown for industry and construction. So that's why it didn't react a lot during that. The index didn't react a lot in March. Also, the accuracy of the index depends on response rates. I mean, it does depend. This is the same for almost any indicator. I mean, you need to have a high response rate in order to have an accurate index, you know. And for example, for the economic sentiment indicator, it happened that, for example, for Italy, it wasn't released in the month of April due to lockdown, due to the lockdown, because they didn't they couldn't collect the answer for the surveys. Another limitation of confidence indexes in general, which doesn't have to, I mean, it doesn't have to be, it's not related with the COVID crisis, but it does exist, is that confidence indexes could show some bias along the business cycle. For example, if we observe the average growth rate of Spain during the 2000 and 2007, the yearly average growth rate of the GDP was 3.7%. Okay, and the level of the economic sentiment indicator was on average 105. Okay, then if we observe what happened during the period between 2014 and 2019, we will see that the GDP growth was 1%. The average GDP growth was 1% less than the periods I mentioned before, but the level of the economic sentiment indicator was higher. Okay. This could be explained because when people are answering the question in the surveys, what matters a lot also is the base period you have. Okay, I mean, it's not the same if I come from the 2008 recession and I have to say how my business is going right now than if I didn't have a crisis a few years ago. You know, maybe it's one explanation why the level of the economic sentiment indicator is so similar, even though the GDP growth was lower. So what we do here is basically, given that the necessity we had at that moment in March of having an accurate indicator at that moment, we start to work and we end up with the indicator that I'm going to present, which is based basically on newspapers articles. And we name this indicator as the daily economic news sentiment indicator, which is based on newspaper articles, which are published every day. So which we are able to construct this index on high frequency and in real time. So we will be able to have an index which is a daily index. Also, given that this is based on newspapers, we will be sure that the index refers to the whole month, not only to some days of it, some days of the month, as it happened with the economic sentiment indicator. And since it's based on articles, which it's supposed to be to express experts' views in a way, the bias I was mentioning before, it's less likely to occur. So we observe here this in this plot, in the left plot, is the economic sentiment indicator. We see that the level of the economic sentiment indicator is basically the same between the two periods I mentioned before. This doesn't happen with the index I'm going to explain in a moment. And also, if we observe March, the economic sentiment indicator, as I said before, didn't react on March. The index we are proposing here, it did, in fact. So we are not the first one which are proposing a newspaper-based indicator. I mean, maybe the most famous one is the Economic Policy Uncertainty Index of Baker and co-authors, but also Shapiro and co-authors propose a sentiment index, which is based on newspapers, articles, and they compare their index with the US Consumer Confidence Index. Also, the newspaper-based indicators are used in order to forecast or nowcast the GDP. Some related works are the one of Thorfruth for Norway or Bertoli and co-author for France. So how do we build our index? Basically, we rely on 5 Spanish newspapers since 1997 and up to now. And we collect this data from Factiva, and we restrict to articles in the Spanish language, articles whose content is related to Spain, based on Factiva's indexation, and articles about financial and economic or corporate news, according to Factiva intersection, okay? So we count all articles that satisfies these three restrictions. Then we split and we count the articles which talk about that the economy is going well, and those articles that talk about that the economy is going bad in a way. So to differentiate between the two, those articles which are talking about that the economy is going well are those which include basically the word Spain, followed by the word Spain and the words and some words which are related to or recovery or acceleration or expansion, and this word has to be between 5 words of the word economic or economy. Okay, the same is for those articles which are talking about that the economy is going bad. They should include the word Spain, and then they should include the word recession or crisis or deceleration or contraction between 5 words of the word economy or economic. So we follow the procedure of Baker et al., of Baker, Bloom, and Davis when they built the Economic Policy Uncertainty Index. And what we did was basically we subtract the number. I mean, we subtract the numbers of articles which are talking about that the economy is going bad to the numbers of articles that are talking about that the economy is going well, divided by the total number of articles. We standardize for each newspaper that series, so that the volatility across newspaper is comparable. Then we average across the newspaper, and then we rescale the index to have a zero mean in the period between 97 till February 2020. So at the end, the index that we have follow really closely the dynamic of the economic sentiment indicator. And as I said before, we think that we are, I mean, we don't think we are having the problem of the bias that I was mentioning before that the economic sentiment indicator has, and it was able to react to the COVID crisis very fast. So even though the index that we have built is closely follow the dynamic of the economic sentiment indicator, we also wanted to know if that indicator helped in a way in order to nowcast the GDP. So what we did is we rely on a mixed frequency B-bar model. I mean, we first compute one of the models will include the GDP and the economic sentiment indicator, and the other model will include the GDP and the daily economic news sentiment indicator, the indicator I'm explaining right now. So under these two,
excuse me, we have 3 minutes.
Okay, so we estimate we do a real-time exercise for computing the nowcast of the GDP, and then we compare the results between the two models. So what we have is that the model that includes the daily economic news sentiment indicator does it better from, I mean, for this period from 2013 till up to March 2020, in the sense that it's the root mean square error is significantly lower for the daily economic sentiment indicator than for the economic sentiment indicator of the European Commission. Maybe one explanation could be the bias I was mentioning before. I mean, you can observe here and here the difference between the nowcast given by the economic sentiment indicator and the nowcast given by the daily economic news sentiment indicator, which is the red line. We also compute, I mean, in a second application, we estimate the probability of a recession using a model which includes the yield curve and one of the confidence indicator I am mentioning, the economic sentiment indicator of the daily economic news sentiment indicator. This is a probit model. So what we wanted to do here, I mean, where the probability of the crisis depends on on the what we know that when the recession is which we use the dating done by the Spanish Business Cycle Dating Committee. So we compute the probability using the economic sentiment indicator and the daily economic news sentiment indicator, and we evaluate the diagnostic capacity of the model using the receiver operator characteristic curve, the ROC curve. Which basically compares the true positive versus the false positive regarding if I say that if the model says that a recession is there, if it was true, it was truly a recession or not at the moment. Okay, so numbers close to 1 means that the model has a better discrimination of the recessions, and it's close to 0.5, it does not. So the only thing we wanted to show here is that both models, the one that included the economic sentiment indicator and the daily economic news sentiment indicator, does very well in forecast the recession in between 5 or 6. I mean, between the whole period. But the daily economic news sentiment indicator does it a little bit better. Then
we have 1 minute to finish.
Okay, I'm finishing. Then we did a real-time exercise trying to estimate the probability of recession using the daily economic, the over-index and the economic sentiment indicator. And you know the probability of recession increased a lot when we focus on the COVID crisis. The probability of recession increased a lot when we use the daily economic sentiment indicator, because we have more a higher frequency for that series. Just to finish, this is how the daily economic news sentiment indicator is on a daily basis, and we can observe here by the end how it behaved. And I have to say that we are using a lot this index at the Bank of Spain in order to follow the economic activity in real time. I mean, at the daily basis. So if you have any question.
Thank you. Any questions?
Can I have a question? Oh, go ahead.
Thanks. I was just wondering if you have any uncertainty measures, or if you could calculate some uncertainty measures around your indicator, because it might also be informative. It's not just a big drop, but how certain it is that it's a big drop, or it can be even a bigger one. Yeah.
Okay. No, we don't have any. At the end, well, I mean, the index at the end is just a count of the number of articles, you know.
Yeah.
So I won't be sure how to compute the certainty around that counts.
Yeah, I'm not sure either. I mean, you could basically look at the variance between the newspapers, maybe. I mean, you have only 5 newspapers, so that's quite crude, but yeah. I was just curious whether you thought about that.
Yeah. Okay, thank you.
Can I ask a question?
Yes.
Thank you, Matthias. I like the presentation. So I was wondering if how your proposed indicator performs against a very simple benchmark model, like an AR model, not in terms of predicting recessions, but rather, you know, the GDP headline figure.
Yeah, I mean, given that the economic sentiment, for example, in the I don't know if you are referring to the Nowcast exercise, for example.
Mm-hmm.
Yeah, okay. So given that the economic sentiment indicator already beats an R model, we are beating, I mean, in the same kind of model, you know, I was talking about before. I mean, if we put the B-bar model using the economic sentiment indicator against an R model, the economic sentiment indicator beats an R model. Okay, R2 2 models. Okay.
Okay.
So given that the economic sentiment indicator beats a very simple autoregressive model, we think that, okay, we have to check it, of course, but we think that our index has to also beat
Okay.
the very simple.
Okay.
Okay, we have to leave it there for the moment. We're going on to the second speaker, Barris.
Yeah.
Barris, you can start.
Yeah. Let me share my screen. Okay. Today I will present Nowcasting US GDP using gated recurrent units. This will be a preliminary result. Okay, I don't have the full result, so I will present the preliminary initial results, and I hope to get feedback from these results. Okay. So all you know that gross domestic product is the most important economic indicator for nearly all market participants. But the problem is the quarterly gross domestic product is released with a delay. Therefore, academic actors need to infer the current state of economy by analyzing data released in a more timely and at a higher frequency data than GDP. Therefore, usually we need a framework that combines high frequency and more timely variables to nowcast gross domestic product. And in this study, we propose such a methodology based on a recurrent machine learning model called gated recurrent unit. As you know from the literature that many nowcasting methodologies has been proposed in the literature. Mainly the initial models, the bridge equations, mixed data sampling models, dynamic factor models, even Bayesian vector autoregressive models. And in our current time, the most of the central banks and investment banks focus on dynamic factor models. They use dynamic factor models as they can overcome a few problems at the same time, like ragged edge problem, mixed frequency data problem, and large scale data set problem. And dynamic factor models can solve all these models in a joint framework so that we can also compute news decomposition. So we can compare the inputs with the actual release data, the experimental data, and we can compute the news, the surprise index. But one of the problem of dynamic factor models and all other regular linear econometric models, they are linear and parametric models. But through the data generating process of macroeconomic variables is usually unknown. So a non-parametric and non-linear machine learning models may be more appropriate for nowcasting macroeconomic variables. However, for nowcasting, there are only a few studies that utilize machine learning algorithms. One of the early works conducted by Kornek and Mikol used linear quadratic discriminant analysis, decision trees, and support vector machines to nowcast the direction of French GDP by utilizing a quarterly data set, including business surveys. And they show that linear discriminant analysis outperformed other machine learning and benchmark models. In another early study, which is conducted by BAU, they utilized a quarterly dataset again that contained only soft data to nowcast Euro area GDP with a random forest. They don't actually show that the random forest is the best model, but they show that if you select variables according to the importance metric of random forest first, then use these variables in a linear model, they provided good nowcasting accuracy. In another study, which is done by Richardson, they also adopted a quarterly large-scale dataset, including 500 domestic and international variables, to nowcast New Zealand GDP with various machine learning algorithms. They use like k-neighbor regression, boosted trees, elastic nets, lasso regression, reach, support vector machine, and neural network models. And according to their results, most of the machine learning models outperform linear models. And among these machine learning models, support vector machines and neural networks had the best performance. Up to this point, all these three models use quarter data and disregard both mixed frequency data problem and rect edge data. Okay, by disregarding the mixed frequency, they lose the information because they only use quarter data, and by disregarding the rect edge data problem, they couldn't compute the news. So, which is why dynamic factor models are so popular. They can compute also the news, the surprise part of the announcement, both the explanatory variable and GDP. In a relatively new study, Lorman and Mas use the monthly scale dataset. So they now switch the monthly dataset to nowcast US GDP with a feed-forward artificial neural network. But for solving the rect edge data problem, they adopt a auxiliary model like bridge equations. So they use autoregressive moving average models to fill in missing values at the end of the sample, and they show that machine learning models outperforms dynamic factor models and performed as well as professional forecasters. And in one of the again recent studies, Soybigen and Yazgan also used the FredMD dataset. Instead of using the machine learning models, they use tree-based ensemble models. First, they utilize a dynamic factor models to reduce both the dimension of the dataset and to solve the rect edge and mixed frequency data problem. Then they feed these dynamic factor models to the machine learning models, and they show that these factor augmented machine learning models provide improvements over regular linear models. So here in this work, we will use a recurrent neural network model. Recurrent neural network models are beneficial for time series forecasting because they allows us previous outputs. They allows us to use previous outputs as inputs. So we can define a regular RNN just like this. So we have a hidden state which consists of which take input as the previous hidden state and input variables. Then we take this hidden state and take an activation function and find the dependent variable, and we can show these regular red RNNs as just like this. These are one layer RNNs. We can also increase the layer of the RNNs. It is very simple. You just stack the RNNs and the mathematical formulation just very similar, so it doesn't change that much. But there's a problem with RNNs. The most important problem is the vanishing gradient problem. So we cannot build big RNN models without coming across with vanishing gradient problem. So there are two important models proposed in the literature. One is long short-term memory, and the other is gated recurrent unit. In this study, we focus on gated recurrent unit instead of long short-term memory. There are two reasons for this. Because GRU, the gated recurrent units, needs less parameter than LSTM and computationally less expensive. So LSTM has 4 different gates and GRU has 2 gates. So you can see the mathematical equation here. So the important part is the upper part. We have 2 gates here, update and reset gates. Update gates allows us to bring information from past. So this deals with the vanishing gradient problem. And reset gates allows us to forget the current information, and we use the regular this hidden layer to update our current information. So this is our methodology. This is the initial methodology, let's say that, because you can use gated recurrent units to solve the rect edge data problem in several ways. So as a start, I use this method technique. How do I do this? So let's assume that F is my key layer GRU model. Okay. So starting from the balanced part of the data set, I can iteratively predict both missing GDP and monthly explanatory variables. So let's assume that in a month, I have both missing monthly explanatory variables and I have available explanatory variables, and I have missing gross domestic product. But here there's a catch. I assume that gross domestic product can be seen as monthly. Okay. So here in the right hand side, previous month GDP, previous month missing variable. So I don't see the explanatory variable this month, but I see it last month, and available explanatory variable this month and previous month. So it's an AR1 process, something like this, or VRL1. And in the left hand side, I can get this month GDP, monthly GDP, and this month missing or unobservable monthly explanatory variable. So I solve the rect edge problem as follows. Also, I try to solve the mixed frequency data problem by converting quarterly GDP to monthly GDP. So I am trying to solve these problems in a joint framework like this. Okay, this is not maybe the best solution for especially for the mixed frequency, but I try to solve it for this for now like this. So
you have 5 minutes.
Yes. So I use the FredMD dataset. For obtaining monthly GDP, I follow the procedure done by IHS Markit, and all variables are transformed to ensure stationarity. I don't use vintage data for now. I use PUSLA real-time data. I use expanding estimation window. I don't conduct that much hyperparameter optimization. So I just select Guru 1 layer and 2 layer with 64 neurons as first layer and second layer 32 layers. If I use dropout, I use 0.2. I use 50 epochs and run the models 50 times, then take the average of all the results. Okay, so let's look at the results. First result. First, I focus on the last financial crisis and around that time, and I have root mean square errors and mean absolute errors. You can see that nearly all my GRU models are better than dynamic factor models, and I estimate this dynamic factor model following Giovanni's methodology. Okay, Giovanni 2008. And you can see that the best model is 2-layer GRU with dropout technique. Here I write with recurrent dropout. There's a different technique called with recurrent dropout, and here in this one I use both recurrent dropout and regular dropout, but recurrent dropout initially worsen the results compared to regular dropout. And here my other results, the figure, you can see that it regularly follows the GDP very well. There are some periods which I miss. Here is March 2011 and September 2011. Okay, so these are the results with dynamic factor model. But dynamic factor model can be also improved. This is just unimproved dynamic factor model. For example, I can use GDP now, which is a very well known dynamic factor model, which also use indirect nowcasting. So first it nowcast the components of GDP, then combine it. So it's a powerful dynamic factor model. Here you can see that powerful dynamic factor model, which is use an indirect nowcasting technique, outperform my model. It's unexpected because it's initial result and I don't use any hyperparameter optimization, but still I outperform the Giovanni's regular dynamic factor model. And if you see the results here, maybe until 2016. I start from 2012 because GDP now started 2011. Until 2016, I have comparable results with GDP now, but GDP now, especially with GRU, between 2016 and 2018, I have some problems during that period, and I should probably increase that part of my model. And this was my initial results. I should really improve the my models, but this is like a showcase. I show that initially it can beat the regular dynamic factor models, so it has improvements and it has a value. Also, I can use Nowcasting GDP and explanatory variables in a joint way. So what should I do in the future work? I don't write conclusion, but I will write the future work. I will use vintage data to have a better Nowcasting exercise. I will use hyperparameter optimization to improve my gated recurrent units. I will use data smoothing because in some studies I show that when you pass a filter among variables, you increase the forecasting results because noisy data, especially when you use machine learning models, can really decrease your Nowcasting accuracy or forecasting accuracy. Here, I first convert quarter GDP to monthly GDP to combine GDP into my GRU, but I try to integrate this in a more natural way, at least try to. And I can also use different techniques, that iterative procedures, to solve the rect edge data problem, and I will also experiment with these techniques. Okay, thank you for listening to me. If you have any questions or feedback, I would be happy to answer.
Thank you. Any questions from the audience? So I have a question. So you showed on your results. So you are producing quarterly GDP forecast or nowcast at a monthly interval. Is that what you're trying to do? You're still doing the quarterly GDP, but at a monthly interval, right?
Yeah, I do like this. First, I forecast the monthly GDPs. Then, when I obtain now monthly GDPs, I just convert that into quarterly GDP by taking averages, then compare the growth rates. So okay. I have monthly GDPs, but to compare it with the actual results and the GDP now, I convert it to quarterly ones.
All right, thank you. Any other questions from? I'm looking at this graph you're showing here. I see you are competing with the other forecasts or nowcasts. So the solid dark curve is the actual GDP growth.
Yeah.
I see some places you are actually doing. I'm only looking at your nowcast forecast in relation to the actual GDP. So in some places you seem to work very well, but in other places, like in the middle, they can miss quite a bit. And not only your results, but other results also can miss a lot.
GDP now also miss a lot, especially.
Right. So that's it's always interesting what makes the difference. Anyway, but it's interesting attempt to use this technique. All right. If no other questions, shall we move on to the next speaker? Thank you, Paris. Next is Tamas Kish, right?
Yes, thank you.
Okay.
Let me.
So I'll remind you at 5 minutes and about 1 minute, okay?
Yes, that's great. Thank you very much.
Okay, thank you.
So thanks for listening to my presentation. I'm gonna present this paper called Nowcasting GDP Growth, allowing for Garch effects and non-Gaussianity international evidence. And I should say this is a joint work with Per Österholm and Farooq Javed here in Örebro University. So as probably needless to say for this audience, that nowcasting output growth is a key issue in macroeconomics, both from an academic and policy perspective. And what I would like to draw the attention to is that recently there has been an increasing attention on the shape of the output growth distribution. So not only the first and probably second moments, but also higher order moments. And this is important for both from density forecasting and fan charts point of view, but also I think there is an increasing interest in what happens in the tails of the output growth distribution. Concepts like growth at risk have appeared recently. So fat tails in the unconditional distribution of the output growth has become a stylized fact, and we basically start from this observation in our paper. And what we do here is that first we provide some international evidence based on a few countries that output growth is indeed characterized by heavier tails. I mean, the distribution of output growth is characterized by heavier tails than Gaussian distribution. But we want to go one step further and want to investigate where these heavy tails come from. And we try to disentangle it into time-varying volatility, which can in itself cause heavier than normal tails in the unconditional distribution. And alternatively, non-Gaussian innovations can also cause non-Gaussianity in the unconditional distribution. And we find that time-varying volatility is an important factor in creating the non-Gaussian behavior. And in fact, if we take into account that the volatility of the output growth might be varying over time, we are able to improve upon density forecasts. But for density forecasts, the role of non-Gaussian innovations is more ambiguous. So this paper is a purely empirical exercise. We just look at what the GDP growth data say from 6 developed countries, and we consider a time period between 1979 and 2019, mostly dictated by data availability in all the countries, but we also experimented some other periods, and the results seem to point at the same direction. So just some descriptive statistics. This is the distribution of output growth in the 6 countries that we consider. And what I would like to point out is that the kurtosis is larger than 3. So this is larger than implied by a Gaussian distribution for all countries. And unconditional non-Gaussianity is rejected for all countries. The evidence is weakest for Australia and strongest for UK and Japan. And this is how the unconditional distributions look like. So basically you see peaks in the middle and tail observations in the tails of the distribution. These histograms also reveal there is some level of skewness in these distributions, but this we do not address in this paper. So the empirical modeling strategy is very simple. We consider basically a benchmark model for GDP growth, for the level of GDP growth, an AR1 process. And what we add here is that instead of homogeneous Gaussian innovations, we allow for the innovations to be heteroscedastic by a Garch-11 specification, and or the standardized innovations could be drawn from a normal distribution or a heavy-tailed distribution, which we here capture by a t-distribution estimate with an estimated degrees of freedom. And our strategy to disentangle the sources of fat tails is basically estimating this simple model and shutting down either the volatility or the non-Gaussian innovation channels and see how results line up. So just for the in-sample results, this is for normally distributed homoscedastic innovations. And here, what I would like to point out is that the LM Lagrange multiplier arch test indicates that GDP growth is indeed characterized by time-varying volatility, less so in Australia and France, but still quite strong evidence for time-varying volatility in other countries. And the Shark-Bera test implies that innovations in output growth from this very simple model are non-Gaussian. However, if we estimate the full specification, so both allowing for time-varying volatility using the Garch model and the t-distribution with an estimated degrees of freedom, what we see is that first, so Garch parameters are quite significant for all countries except France. So Garch seems to be a more general feature. So time-varying volatility seems to be a more general feature of output growth innovations, while after controlling for time-varying volatility, the evidence for non-Gaussianity in the innovations is less clear. So 4 out of the 6 countries, Australia, Canada, France, and Japan, they exhibit they have high estimated degrees of freedom, so their innovations are close to normally distributed. However, for UK, for the United Kingdom and the United States, you see low estimated levels of degrees of freedom, and hence, even after controlling for stochastic time-varying volatility, we still find that residuals, standardized residuals, have a non-Gaussian distribution. Okay, so in sample, we find some mixed evidence, but still many significant results for especially supporting time-varying volatility in output growth. But our question is also, I mean, if we want to model GDP growth and forecast it, how does accounting for these features impact the forecasting performance out of sample? And for that, we perform a very simple expanding window analysis for each country, where we look at only nowcasting, so short-term, 1 period ahead forecasting, basically, and we consider both point and density forecasts. The forecast evaluation is very standard. What we use is, for point forecast, we use mean squared error, root mean squared errors, and corresponding Diebold-Mariano statistics. And for density forecast, we use the concept of probability integral transform introduced by Diebold and Cotters 1998, which has been used as a measure for how good our density forecasts are. So in particular, the distance of this probability integral transform from the uniform distribution over the unit interval is basically a goodness of fit measure of the density forecast. So the lower the distance, the lower the distribution of the probability integral transform, or the closer the distribution of the probability integral transform is to a uniform distribution, the better density forecasting model we have. We use to measure the distance between the PIT and the uniform distribution. We use the Kullback-Leibler distance between distributions, but we also consider test statistics of some formal tests of equality of distributions, like the Kolmogorov-Smirnov or the Anderson-Darling tests. We do not really, for the density forecast, we do not really consider formal tests we do not really test whether the distributions are equal to the uniform distribution, but we rank our models based on either the Kullback-Leibler distance or the test statistics of the formal tests. So, but going to the results, first point forecasts. And here I would just like to draw your attention to the fact that the RMSEs within a country, whether we consider a Gaussian model with Garch errors, a t-distribution, or a t-distributed model with Garch errors, basically irrespective of the specification, the RMSEs are very close to each other. implying that for point forecast, it doesn't really matter how we model the innovations of the output growth in this simple specification. But this is also not very surprising, since the mean equation, since the estimated parameters of the mean equation are barely affected by allowing for time varying volatility or non-Gaussian innovations in the error term. In contrast, we see big differences for density forecasts. And basically, there are two main takeaways which are mostly uniform over all countries and all measures used. One is that the benchmark model, which is the one with normally distributed homogeneous homoscedastic errors, performs worse. So the first numbers in each, the first row in each for each specification produces the highest number, or in most cases. Once we move from homoscedastic to heteroscedastic, so Garch errors, there is a substantial improvement in terms of density forecast, basically in all countries except for France, where we have seen even in the in-sampler results that conditional heteroscedasticity is not really present. So from going normal to Garch normal, there is an improvement. However, going from the benchmark normal to only a T distribution, to only a model with non-Gaussian innovations does not really improve density forecasts. And then when we allow for both Garch errors and T distribution, then comparing that result with Garch errors but normally distributed innovations, again, we don't see much difference. So overall, what we find is that in terms of density forecasts, it seems that it's important to account for heavy tails in the distribution, but mostly in the form of time varying volatility and less in the form of non-Gaussianity in the innovations.
So you have 5 minutes.
Thank you. I will finish very soon. So just one example of how these density forecast results line up. I show you the result, the distribution of the probability integral transforms for the US. And what you see is that for the normal benchmark model, the probability integral transform is quite far from a uniform distribution. But once we allow for Garch effects, so for time varying volatility, the histogram moves closer to uniform distribution. In case of the US, the T distribution also helps somewhat in itself without accounting for Garch effects. But clearly, the best model in this case is the model where we allow both for time varying volatility and non-Gaussian innovations. And so basically this is all my presentation. So to conclude, our findings confirm the stylized fact that has been noted in the literature that output growth is characterized by fat tails. What we find based on our international evidence that these fat tails or heavy tails are primarily attributed to time variation in the second moment in the volatility of the output growth series, and the importance of non-Gaussian innovations is secondary. And also what we find is that in terms of density forecasting, if we account for heavy tails, in particular in the form of time variation in volatility, then we can achieve an improvement in terms of short-term density forecasts. So thank you very much. I guess it was short.
So you finished early.
Yes.
Any questions?
I always have a question. So thank you for the presentation. I really liked it. I was just wondering about one thing. So you allow for time variation in the volatility through the Garch effect. Have you also tried a stochastic volatility specification?
Yeah. I mean, not in this paper. We are currently working on other projects where we use stochastic volatility.
Mm-hmm.
The results are generally very similar, I would say.
Very similar,
so
right?
Both the fact that it matters and that it also subsumes some of the fat tails. So once we account for either stochastic volatility or conditional heteroscedasticity, you find that the remaining standardized residuals are not that heavy-tailed any longer. Yeah.
Right.
Thank you.
Right. So the main improvements actually come from the time variation in the variance.
Exactly.
Right.
And I think that's kind of an potentially important policy conclusion when, I mean, once allowing for stochastic volatility, the further room for improvement in higher order moments is relatively small. Of course, this is only GDP growth, so I'm not saying it can be very different for other variables, but for output growth, at least that's what we find.
Right. Thank you.
Thanks.
Any other questions? We have a couple minutes. So if no questions, should we proceed? The last presentation will be my presentation. I will not share my screen. Let's see, share. You know, I have a hard time to do this. I lost it. How do I get my screen back?
Actually, you are sharing your screen now.
Yeah, you
I'm
are.
sharing my screen.
Yes, you are.
Yeah.
You see it? Okay, good.
Yes, exactly.
All right. Okay. Let's. Can I still do? No, I cannot do. I can do it. Okay.
Perfect.
So this is a project that I did with my colleague at U.S. Bureau of Economic Analysis, and Barry's early on talked about using machine learning to nowcast GDP. This is a different approach, but also it's nowcasting a component of a GDP. So quickly, and this project explores individual and combination forecasting techniques for improving the accuracy of the first, or we call the advanced estimate of private consumption of services at the very detailed component level in the US national account. So I'll go straight to the motivation. And we all know GDP measures economic performance of a nation and is a very important source of information on how the macroeconomic conditions are evolving. So it is very important to have timely and accurate estimates of GDP. And that's important for decision makers in business and in the political arena. So in the United States, for each quarter, GDP is released 3 times, and there's 1, 2, 3 months, respectively, after a quarter has ended. So there's at least a delay of 1 month for the first or the advanced estimate. So because of the timing of the quarterly source data, the early estimates, especially the first one, are primarily based on very limited and incomplete indicator data. So these estimates are often later revised. So if we look at the makeup of GDP, we see the big components are consumption, investment, government spending, and export and imports. And in terms of consumption, which takes about 2/3 of GDP, and 2/3 of consumption is actually consumption of services. So that's a biggest subcomponent in GDP as a total. So in this study, we focus on to improve the accuracy of early estimates of consumption of services. So because GDP is built up from the detailed components, so the techniques that we consider have to take that into consideration. And the quarterly source data for services is the quarterly service survey conducted by a Census Bureau. So these estimates are not available for the first estimate, and they are partially available for the second estimate, and they become available for the third estimate. However, not every component has a quarterly source data. Because of the timing of the quarterly source data, the first estimate basically are compiled using monthly indicator data. The monthly indicator data are assigned by the national accounts. However, we have an insufficient number of relevant indicators for all detailed components. And also the indicators we currently use, and there is a lack of a correlation between the quarterly source data, which is QSS, and the monthly indicator. Therefore, so the first estimate or the advanced estimate often later are revised. Here are some examples. So we can see here are some examples of detailed components. The red line is the first estimate. These are the standardized growth rates. And the green line is the third estimate, which is the last of quarterly estimate. And the blue bar indicates the revision from the third and the first estimate. So we can see sometimes the revision can be fairly large, can reach more than 3%, sometimes approaching 4%. So, there is a need to try to improve the accuracy of the first estimate so that the revision gets smaller. Currently, the advanced estimates of a detailed PCE, we call it personal consumption of services, they are compiled using a simple extrapolation method. We use the percentage changes in the monthly indicators in the current quarter only. So this technique does not utilize information on the longer, medium, or short-term behavior of the quarterly target variable, which is the component itself, and also does not take into account of the longer and medium-term behavior of the indicator variable. So motivated by the performance of the current method, we would like to explore other techniques that can improve the accuracy of the first estimate. We would like to use more information that we can reflect a longer-term trend, medium-term dynamics, and short-term or medium-term cross-sectional behaviors of the components. So in this study, we consider two types of nowcasting approaches. One is individual model. So in that, we consider bridge equation and bridging with factor model. And then we also consider a set of forecasting combination techniques and to see if combination techniques will improve upon individual models. To evaluate the performance of each method, we split the sample into estimation or training set for in-sample estimation. And then we also leave a test set for evaluation. And we use pseudo out-of-sample predictions from each technique. And we also use real-time data so that we can compare the performance of each method with the current extrapolation method used in the national account. And I think these two equations are very familiar to everyone. The first one is the bridge equation model, and this component is the quarterly growth rates of the monthly indicators. And so this is a very widely used bridge equation to bridge the monthly indicator into the regression for the quarterly target variable. They also use the lagged target variable to the piece lag. So the bridging with factor model replaced the monthly indicators with the common factors extracted from a factor model. And the advantage of that is you could use a much larger set of indicators to get some common information for the service sector rather than using one or two indicators and assigned by the national account. So in terms of the combination techniques or model averaging techniques, we consider the following. We have 4 averaging schemes with mean, median, and trimmed means. We take out 10, 25% top and bottom value the estimates before we do averaging. We also have 3 information criteria based averaging, AIC, BIC, and also the non-penalized log likelihood function averaging. And it's actually very interesting to see what the unpenalized information criteria averaging will bring to the results. We'll talk about later. We also have model fit-based averaging. We use a Bayes Granger, and here we use the leave one out arrow in combination with Bayes Granger. And we have also tried 2 quadratic minimization type of averaging, jackknife averaging, and also mallow averaging. And we want to see the sophisticated averaging techniques, whether they will bring some contribution to the results. So we have a basic bridge equation and bridging with factor models. In those 2 basic models, we allow up to 4 lags of the indicators and the quarterly target variable, or 4 lags of 2 factors we extracted from the factor model, and 4 lags of the target variable. And let the program to decide and how many lags are actually needed. And based on the 2 basic models, we also specified the 5 bridge equation model and 5 bridging with factor models. To distinguish each model, basically the number of lags allowed in each model is different, as specified here. So then the model averaging technique will average the estimated model. So the data used in the estimation, we have 88 service components from 9 service categories. We use real-time data. We have quarterly estimates from 2009 Q3 to 2019 Q4, total of 42 quarterly vintages. And in combination with the 126 monthly vintages, they're used to compile the estimates. In a factor model, we collected 92 monthly indicators from the 9 service groups, trying to get some common economic condition or business condition in the service sector. So we split the sample into in-sample estimation set. That's from 2009 Q3 to 2017 Q1, 32. And then we use the rest for out of sample, pseudo out of sample prediction and to do the evaluation. So as I said, in the in-sample estimation for the bridge equation and bridging with factor models, we allow up to 4 legs of a target variable and indicator all the common factors. We use the status V select, and the best model is based on the AIC corrected for small sample. And then we also use the 10 specified models for model averaging using the techniques I outlined before. So in terms of the pseudo auto sample predictions, we use an expanding window design to, to best take advantage of our very short time series. Basically, we estimate the model. We're using, for example, here, we're using data to the end of the estimation set, and then we predict the first quarter out of sample prediction. And then we increase the estimation set by 1 observation, then we re-estimate the sample, then we do the second prediction. So we go to all the end to the 11th prediction. So to evaluate the performance, we use root mean square revision, and we also look at the mean absolute revision from the 2 individual method and also the 10 model averaging techniques. So just quickly mention for the 2 individual models, the results shows that even though we allow up to 4 legs of the target variable and indicators, and not 4 legs are used, but some legs and different legs are used for each component, and the characteristics of each component series determines what is the best model. And also here, so we're going on to the out of sample prediction for the bridging equation and the bridging with factor models. And there are 73% of the 88 components, which is 64, we see reduction in the revision, in the root mean square revision. But here I want to focus on the model averaging techniques and the results. So the general observation of the combined predictions, also we see characteristics of each component determines which model averaging technique will produce the largest reduction in root mean square revision or a mean absolute revision. So including model averaging techniques and in combination with the bridge equation and bridging with factor model, we're able to reduce reduction in terms of root mean square revision in 80 out of the 88 components. And interestingly, the non-penalized log likelihood averaging outperforms all other methods and is selected as the best model for 40 out of the 88 components. And the bridge equation and bridging with factor models combined are also selected for 17, which is about 19% of the components. So, and then there are simple averaging techniques that covered 13 out of the 88 components. And the other more sophisticated techniques like jackknife and mallows actually didn't really do an outstanding job in using this data. So also the degrees of reduction in root mean square revision from the model averaging techniques are generally larger than those from the individual bridge equation and bridging with factor model. So here's a quick example of just one group, healthcare services. We look at the percentage change in root mean square revision from all the techniques. And in the last 2 columns, there are best bridge equation and best bridging with factor model in the last 2 columns. And we see out of the 20 components in healthcare, And log likelihood averaging actually account for 13 components selected as the best technique. So this is one example of one group of services, and it's one of the large groups in services. And so here is a summary of the service groups. We lumped a couple groups together. So now we have 7 categories here. And we can see the number of components add up to 88, 100%. And the current method, extrapolation method, is still considered better than the rest of them in 8 out of the 88. And the likelihood averaging accounts for 40 as the best method. And we can see the distribution of different combination techniques and individual model and bridge equation bridging with factor models. So this is the selection of a best model for each category of services and from our data. And here we see we have again 88 components. We have the current method still takes 8 as the best method, and we also have 9 and 8 from the individual models that we looked at. And we look at the largest reduction in root mean square revision for model averaging methods. They count for 63 out of the 88, which is 72%. And the ranges in the reduction in root mean square revision is from smallest 2.3% to 63%, could be very significant. So here are quick examples coming to the end of the time. So here we see the blue lines are the prediction revisions from our models. Here, the first one is a bridge equation model, and the one below is also bridge equation model. On the right column, the 2 are from bridging with factor model. We can see using the nowcasting techniques, revisions are smaller and smoother. Here are some examples of the model averaging techniques. Again, we see the revisions from the model averaging techniques are much smoother and smaller than the current technique. Finally, this is my last slides, and so we have shown that the potential usefulness of nowcasting techniques for improving the accuracy of advanced estimates of detailed personal consumption of services because they allow all available information to be utilized in estimation. Using individual models alone, we can reduce root mean square revision in 64 or 73% of the components. By including model averaging techniques, that increases to 80 out of 88 or 91% of the components. So we can see actually the model averaging techniques and the individual nowcasting models, they have the potential to be a powerful tool in reducing revisions in national account statistics and at a very detailed component level. So currently, especially during this pandemic months, several months, and there is a much more delayed collection process of monthly indicators. So the national accounts is considering using credit card payment information in addition to the monthly regular indicators from the government agencies. So, however, right now, the national accounts still produce the first estimate using the extrapolation method. And then on top of that, they make some adjustments, which I think is a short-term strategy. So our next step is to include credit card payment data in the model to capture a broader range of spending activities, and especially during sudden changes in the economic conditions, such as we are experiencing now. So we want to see if credit card payment data bring in additional information and can further help improve the accuracy. Thank you. That's the end of my presentation. Any questions?
I would have a question.
Yes.
Sorry. Yes. So thank you for the presentation. I really liked it. I was just wondering if there's a way to somehow get you know, density forecast or some sort of an uncertainty measure you know, for the individual components, if that would be possible, or if you have thought about that.
You know, I think first of all, we have a very short time series data, and we have very detailed components. And so, you know, we thought about the techniques that will be easy and straightforward to be implemented in the production. Right now, actually, we are doing the parallel testing. We have been doing it for several quarters. So we looked at predictions up to 2019 Q3. And then we selected the best model. Then we actually doing the real out of sample predictions. However, we are, you know, running into a terrible time. We have the pandemic, and the national accounts, they do adjustment on top of their estimation, which they use data we don't use. We don't know what they're using. So it's hard to compete, but we're still doing like 50% of our predictions are better than, you know, in terms of revisions, than they are doing the afterwards adjustment. So we think there's a potential. I think the special feature of this research is that we have to keep in mind, we're looking at the bean counting nature of national count. You have to be responsible for every component. And I think the density nowcasting sounds a very interesting technique. I've listened to and read about that, but we have not attempted to use that for individual components. But maybe in the future research we will. I think our main task is to figure out whether we can select some of the model averaging techniques, actually use it in the national, you know, statistic production. So that will be actually a pretty significant change in the way we produce the estimates. But it's an interesting suggestion. In the summer, especially in GSM, there's a session. Almost most of them are talking about density nowcasting and the ways to compare the accuracy. Very, very interesting. Yeah. Thank you for that suggestion.
Thank you. Thank you.
So I guess if there are no questions, we'll end the session.
Just one question.
Okay.
Are these forecasts going to be published, or are they for private use?
Now it's still in the research stage. We're doing the parallel testing. We want to do 1 year parallel testing to see if our predictions and you know, what's the degree of improvement in the revision using our techniques. Because right now we have 12 techniques, 10 model averaging techniques and 2 individual models. We need to narrow down to a small group of methods and build a computer program, so the analysts can, you know, have very straightforward criteria to choose and what to use. So to to go from research to production, and the national accounts have to be very, very careful because, you know, this is big change in the way we do a first estimate.
Thank you.
Thank you. All right, I think that's, if there are no questions, then we end the session. Thank you.
Thank you all.
So we'll click leave, right?
Exactly, and leave end meeting for all.
Okay, all right. So I'm gonna leave here. Thank you.
Thank you.